Today's talk will be given by Yang Ku. Thanks for being here despite being evening in China. Um, she is from the Peking University and she will talk about exact simulation of self-excited point process with Levy driven or stimulate intensity. Thanks a lot.
Yeah, okay. So thank you for inviting. So today I'm going to talk about my research on exact simulation for self-excited point process with Levy Driven OU intensities. So here is the outline. I will first introduce the Levy Driven OU process and introduce how to develop exact simulations for this process. And then we will consider the self-exciting point process with the exact simulation scheme. Then we will check the numerical results and discuss something about the applications in finance and insurance for the point process. So for the Levy-driven OU process, we have XT being the Levy-driven OU process. It satisfies the stochastic differential equation in equation 1. So beta rho here is the positive constant. Delta is the constant decay exponential decay rate. So instead of the standard Brownian motion, we considered Levy subordinator here ZT. So we call this background driving Levy subordinator. It can be some typical examples is it can be a gamma process or it can be temporal stable process. So we get the Laplace transform for the Levy-driven OU process. It satisfies equation 2. So in here, this phi of u is the Laplace exponent of this Levy subordinator, with v being the Levy measure of the background driving Levy subordinator of zt. So we can specify the Laplace transform by consider special case with zt being a temporal stable process. So if we have a temporal stable driving OU process, we call it OUTS process. So the temporal stable process have Levy subordinate as a Levy subordinator, with its measure being specified in equation 3. In here, we have alpha being the stability index, and theta being the intensity parameter, and beta being the tilting parameter. So the corresponding OU stable Laplace transform can be expressed as in equation 4. So to develop an exact simulation scheme for the OUTS process, given the position of the process at time t, we want to know the position of the process at time t plus tau. So we need to know the transition probability of the process. However, inverting this Laplace transform itself is quite challenging, but we will get some information from the Laplace transform. So we have the following results for the distribution of the process at t plus tau condition on xt. So the distribution of the process can be decomposed into a 3 component. The first component is a constant. The second component is a temporal stable process, a random variable, and the third component is a compound Poisson random variable. So the temporal stable random variable has a stability parameter being alpha, and the intensity parameter being beta divided by W. W is a constant, and the rest is the tilting parameter. And the compound Poisson random variable, the jump distribution of the compound Poisson follows a gamma distribution with shape being 1 minus alpha and rate being beta times a well-defined random variable v with density function xv of u. So this temporal stable random variable and the compound Poisson random variable are independent with each other. So we get this by splitting the Laplace transform. So let's have a look at the Laplace exponent of the OUTS process. So we have the OU temporal stable process, and we can, with the Levy measure of the temporal stable in the Laplace exponent, So we can split the process, the Laplace exponent into two parts. So the first part represents Laplace exponent of some Levy subordinator with infinite activity jumps. And the second part represents some Laplace exponent for Levy subordinator with finite activity jumps. So if let's consider the first part first. So if we do some change of integration or substitution technique, we can rewrite the equation 6 as something of the form in equation 8, which clearly is the Levy representation for the temporal stable random variable, and the Levy measure of the temporal stable is specified in equation 9. So we can see is still a temporal stable random variable with shape being alpha and tilting being beta divided by w, and the theta times 1 minus w to the alpha divided by alpha is the intensity. So for the equation 7, we can rewrite this as the form in equation 10. So we verified the dw here is a finite constant. So the thing outside the integral is a constant which is finite, which represents the rate of the Poisson parameter, and the inside the inner integral of equation 10 represents some distribution function of a mixed gamma distribution. So it's a gamma distribution density with the shape being 1 minus alpha and the tilting parameter being beta times a random variable v, with v being some well-defined random variable. So we say this equation 10 represents the Laplace exponent of a compound Poisson, with n being a Poisson parameter being a finite constant, and Si being IID jumps follows a gamma distribution with parameter shape being 1 minus alpha, rate being beta times v, and v is a well-defined random variable with density satisfies equation 11. And this random variable v can be simulated exactly by using the acceptance rejection scheme. So by the decomposition method here, we know how to simulate the temporal stable, and there are existing simulation scheme for the temporal stable. And if we know how to simulate the compound Poisson jumps, then we can simulate the OU-TS process. So the task is to simulate the compound Poisson jumps. So as it's gamma distributed, we only need to do is to simulate the random variable v, develop the exact simulation scheme for the random variable v. So we choose the envelope with density in equation 12, which can be simulated using inverse transformation method. So we have the following simulation scheme for the random variable v. So equation 13 represents the inverse transformation scheme to generate the envelope random variable. And step 3 is the acceptance rejection decisions to generate the random variable v. So with the acceptance rejection scheme for the random variable v, and with the decomposition scheme for the OU temporal stable process, we can generate the corresponding OU temporal stable process. So here is one sample path for the temporal stable OU process. So now we have the simulation scheme for the temporal stable OU process. We will now consider a corresponding point process. So let's first give the definition for the point process with Levy Driven OU intensity. So we have a point process N with stochastic intensity lambda t being a Levy Driven OU process, satisfies the SDE in equation 14. And the corresponding self-exciting point process is defined as the intensity process is defined as equation in equation 15. where we adding a self-exciting component into the intensity process. So the self-exciting component depends on the point process itself. So it only influences the intensity process when the point process, when the event occurs for the point process. So it jumps simultaneously with the point process. So our next task is to develop exact simulation scheme for this self-exciting point process. So before introducing this point process, let's first define the interarrival time. We call the I+1 interarrival time be tau I+1 be the difference of the time arrivals for the I+1 event minus the arrivals of the S event. And we name capital lambda T be the cumulative intensity process. So exact simulating the point process can be reduced to the problem of given the time Ti and the position of the intensity process lambda Ti. How can we exactly simulate the next arrival time Ti+1 and find the intensity level at time Ti+1? So one unique property of the self-exciting process is the self-exciting component for the intensity process will only influence to the intensity process at the time of jumps. So between the two arrival jumps, the intensity process only being a Levy Driven OU process. So for T between Ti and Ti+1, lambda T is just a Levy Driven OU process, which satisfies equation 16. So we can use the following graph to illustrate the idea. So if we are at the position Ti and the S, we know the S arrival time, and we know the intensity process at the S arrival time, which is lambda Ti. So what we want to do is to simulate the next arrival time Ti+1, which is equivalent to simulate the I+1's interarrival time, tau I+1. And before the I+1's arrival time occur, the intensity only follows the Levy-driven OU process. So the position of the intensity process just before the I+1's arrival occur is lambda Ti plus minus. We call it the pre-jump intensity level. And when the I+1's intensity, when the I+1's arrival occur, we will add xi+1's unit to the intensity level, and the position of the intensity level at time Ti+1 will be lambda Ti+1. And we will use this lambda Ti+1 to simulate the next tau I+2 interarrival time. So the simulation question will be equivalent to simulate given Ti and lambda Ti, how to simulate the I+1's interarrival time and the corresponding pre-jump intensity level. So let's first study the distribution for the interarrival time and pre-jump intensity level. So we using the piecewise deterministic Markov chain property, we get the joint distribution of the pre-jump intensity and the cumulative intensity level. So the joint distribution satisfies equation 17. If we set V equals to 0 in the joint Laplace transform, we can get the tail distribution for the interarrival time, which is the result in equation 18. So first, for the interarrival time, we get the tail distribution for the for the interarrival time. So we can express this as the product of the tail distributions of two random variables, V star and VTS star in 19. So if it can be expressed as the form in equation 19, we know that the distribution of tau I+1 is equal in distribution with the minimum of V star and VTS star. So in the tail distribution of V star and VTS star, it specifies in equation 20. And we can get the information from this tail distribution that the VTS star is actually a defective random variable. And we can use inverse transformation method to simulate this defective random variable. And V star is actually the first arrival time of a non-homogeneous Poisson process. And there are existing simulation algorithm called thinning scheme to generate the arrival times for the non-homogeneous Poisson. So here we have the simulation scheme for the inter-arrival time. So first, we generate the defective random variable VTS star using the inverse transformation scheme. And then we're using the simplified thinning scheme to generate the first arrival time of the non-homogeneous Poisson with Poisson rate in equation 21. And so we need to check, because VTS star is a defective random variable, we need to check whether VTS star is infinity or not. If VTS star is less than infinity, then we have tau I plus 1 is equal in distribution with the minimum of V star and VTS star. So if the defective random variable VTS star is equal to infinity, then we directly have tau I plus 1 is equal in distribution with V tau. So no matter what background driving Levy process is, we can use this simulation scheme to generate the inter-arrival time. The tricky part is the simulation scheme for the pre-jump intensity level. So we have the Laplace transform for the pre-jump intensity level in equation 22. So we have three parts. The first part is just a constant Laplace transform of a constant. The second part and the third part for equation 22 are more important. The thing here, because we haven't identified the background driving Levy process of the OU is, so we cannot get the information for the Laplace exponent for the Levy subordinator, and we do not know the Levy measure, so we cannot further analysis the second part and the third part of the Laplace transform of the pre-jump intensity level. So let's consider one special case when the background driving Levy process being the temper stable process. So with the point process with the intensity being OUTS process, so the ZT is a temper stable process with Levy measure specified. So we can have more information for the pre-jump intensity level. Basically, we have the following result for the pre-jump Laplace transform of the pre-jump intensity level. It can be split into several components. The first component is the Laplace transform of a constant. The second component is the Laplace transform of a Levy subordinator. And indeed, this Levy subordinator is a temper stable process. And the third component is the Laplace transform of a compound Poisson with the jump process, the jump size distribution being gamma distributed. And the fourth part is a Bernoulli trail. So let's have a look at the sketch proof. So for the second part of 2022, for this, the second part of 22, we can rewrite this as the following form. We can split the second part, the Laplace exponent, into two parts. The first part represents a Levy measure, a Levy representation for infinite activities, Levy subordinator, and the second part represents the Levy representation from the Levy subordinator with finite activity. So for the first part, it is Levy Laplace exponent for a temper stable process. And for the second part, we can see it is the Laplace exponent for a compound Poisson process, with the jump being a mixture of gamma distribution. So now we have the third part of the equation 22. It's indeed after rearranging the integrals and using substitution and change order of integration, we can simplify the Laplace transform as something like P1 times the Laplace transform of 0 and P2 times the Laplace transform of a random variable S. So this is actually a Bernoulli trail with two outcomes, one outcome being 0 with probability P1 and one outcome being a random variable S with probability P2, and the sum of P1 and P2 equals to 1. So the random variable S is a gamma distributed random variable with shape parameter being 1 minus alpha and with the rate being kappa times V0 minus 1 divided by delta. And the density of this V0 is specified in 27. So this is all we can observe from the Laplace transform in here. So the last line of this slice, we can see this, the inside integral is a mixing gamma distribution. And the part, the part to the power of -1 minus alpha divided by kappa u minus 1 divided by delta to the power of 1 minus alpha is actually the density of the shape parameter for the gamma random variable. So we have the following decomposition result for the pre-jump intensity level. So we decompose the pre-jump into 4 components: a constant, a temporal stable random variable, a Bernoulli trail, and a compound Poisson random variable. So if, as we know the exact simulation scheme for the temporal stable, and the only thing we need to do is to develop simulation scheme for this random variable S and the simulation scheme for the IID jumps SK. So for the random variable S is with the density, we can use inverse transformation method to simulate it. And the simulation method can be specified in equation 30. The slightly challenging part is the simulation scheme for the IID jump for the compound Poisson. So we have the IID jump being a gamma distributed random variable with shape being 1 minus alpha, and the shape, the rate being kappa times V minus 1 divided by delta. So this V cannot directly simulate it using inverse transformation. So we must use a second rejection scheme to simulate it. So we choose the following envelope to simulate this random variable V, and the simulation scheme is specified as follows. So the first step, we use the inverse transformation scheme to simulate the envelope. And then we follow the second rejection procedure with the AR decision in step 3 to generate the random variable S, random variable V. So with the simulation scheme for V and with the simulation scheme in equation 30 for V0 and with the decomposition scheme in 28, so we can generate the pre-jump intensity level for point process with intensity being Levy driven temporal stable driven OU process. So this is the case for the intensity being a temporal stable driven OU process. So we also tried the case with gamma driven OU process. We have the similar result. So the distribution for the jump size distribution for the compound Poisson and the Bernoulli trail are different. But well, you can use inverse transformation and a separate rejection to generate. And we also get, instead of the temporal stable here, we get gamma for the gamma point process with gamma driven OU intensity. So the decomposition scheme works for any Levy driven or any point process with Levy driven OU intensity. The precondition is we need to know how to simulate the background driven Levy process, because after decomposing the pre-jump intensity level, we get one of the results being the background-driven Levy subordinator. So if we don't know how to simulate the background-driven Levy subordinator, we will not know how to simulate the pre-jump intensity level. So the precondition is we need to know how to simulate the driving Levy subordinator in order to simulate the pre-jump intensity level. So for this case, as we have the simulation scheme for the pre-jump intensity level, and we use the simulation scheme for the inter-arrival time, we follow the following procedures to simulate the sample path for the point process. So basically, we start the process at 0, and we first simulate the first arrival time for the first event, and then we using the decomposition scheme to simulate the first pre-jump intensity level, and then we get the pre-jump intensity level for the first event occur. We need to add the first self-exciting jump to the intensity, and simultaneously increase 1 unit for the point process. So following this loop, we will get the whole sample path for the point process. So to verify the simulation scheme, as we get the analytical solutions for the expectation of the point process. So what we did is we compared the estimated mean with the actual mean of the point process to check the accuracy of our algorithm. So the result shows that the algorithm is very accurate. And one remarkable thing is that our algorithm does not introduce any bias or truncation errors, because in the whole simulation procedure, we didn't use any discretization or truncation approach. So there will not be bias or truncation errors for the simulation algorithm. So here is one sample path, some sample paths for the point process with Levy Driven OU intensity. So the first tool is the one without self-exciting component. So we can see for the second graph, for the second sample path, when t equals to 500, there are less than 500 arrivals. But if we add the self-excited component under the same parameter setting, with t equals to 500, we have more than 700 arrivals. So this is how self-exciting component will capture the contagion phenomena we observed. For applications, this point process has many applications in finance and insurance. For example, we can use the contagion process or self-exciting process to model the arrivals of loss for a portfolio of investment. So, and we can use the exact simulation scheme to estimate the corresponding loss process distribution. So if we use the point process to model the arrival of loss for a portfolio of investment, let's define the point process, define the loss process being LT. And this Li is the individual loss, and it happens at the time Ti. This Ti is the arrival of the loss, which modeled by the self-exciting point process. And this Li can either be constant or random. With our simulation algorithms, we can use the multi-column method to estimate a corresponding distribution for the loss process. So for example, we consider the 3 cases with Li being constant, with Li being uniform distributed, and Li being exponential distributed. So the simulation scheme can give the sample path for the point process. We can also have the sample path for the loss process. So the first graph is the sample path for the loss process. And by simulating 10,000 sample paths for different t's, being 1 t equals to 1, 2, 5, 10, and 20, with Li being constant, uniform distributed, and exponential distributed, we can estimate the corresponding cumulative distribution function for the loss process. And it's very flexible. It's not depends on the parameters because, well, the simulation algorithm does not depend on the distribution of any parameters of the Li's and the T's. So since we are estimating the rare event here, we can also apply some variance reduction techniques such as importance sampling to further reduce the variance to get more accurate estimation for the probability of this rare event. Similarly, we can also use the simulation scheme to estimate the ruin probabilities if we use the point process to estimate the event arrivals. So if we have a firm with a surplus process satisfies equation 33 and the claim arrival has been modeled by the Levy Driven OU point process, then we can use our exact simulation algorithm to estimate the corresponding ruin probabilities against the time. So with the simulation algorithm, although we don't have the distribution for the point process, but we can use it to estimate many important quantities in risk management and insurance. So basically, this is what we did for the Levy-driven OU point process. You can so in here we have equation. We have the general simulation scheme for inter-arrival time. The only thing we cannot do general is the general simulation scheme for the pre-jump intensity level. But as we have the Laplace transform for the pre-jump intensity level, so if we can, what we can do is we can do it numerically by inverse the Laplace transform numerically and then develop simulation algorithms. Although the exact simulation is not exact, but you can get a more general simulation for the corresponding point process with more generalized background driving Levy process. Yeah, so basically that's what my talk about today. Yeah, thank you for your attention.